Hey, both of you, how are you doing?
Pretty good. How are you?
I'm fine. We'll wait for some more time. I'll just pause the recording for a while. Start recording again. All right, so it's recording now. I'll share my screen. Okay. So this is the this is the paper that we were supposed to read today. It's mostly gonna be casual reading this paper. Like, what do you think about it, and those kinds of things. Like, you can stop me, and I have a presentation as well, but mostly it's different parts of this paper. So at any moment, if you have any question, just unmute yourself and ask. Okay. There's less people today, so this is not going to be that hard. Okay. So in general, this is again from U Montreal and DeepMind, and this was in 2016. And I'll tell you what the paper is structured like first, and then I'll give you the presentation and show you some videos from the paper, and then we can conclude. So introduction in general, like they're discussing online reinforcement learning. What is the meaning of online reinforcement learning? um, what is experience replay, and what is their method, and how does it have benefits over the other methods. Then in related work, they're discussing Gorilla, MapReduce based approach, and another old approach that they think is related to their work, which uses parallelized learning. So basically, what this work is doing is that it is taking the QLearning algorithm and it's running it on multiple threads. So it's a multi-threaded algorithm, um, not too difficult to grasp. Uh, and then here they give the background of what reinforcement learning means. Uh, what is an action space? What is a state? What is a policy? What is a discounted reward like? What is the action value function, Q function, and the value function? And then yeah, if you have any questions at any moment, just stop me and ask me, and like unmute yourself and ask. Don't worry about it. And uh, then like they discuss, so like if you were here last time, we were discussing this loss formula from QLearning, which is given by the Bellman equation. This part is the part which is given by the recursive update. Like this is the recursive update part from the Bellman equation, and this is the actual value. So actual value minus a target minus actual value, and you take the square of it, and that gives you the loss function to use to learn a Q function. Then here they're talking about uh, how to use policy gradient methods. Like policy gradient is another kind of family of algorithms that is known in reinforcement learning. I'm not discussing policy gradient today, but I will discuss it next time, because next time the paper is DDPG and that's too small of a paper. So I'll discuss policy gradient approaches next time, and DDPG. Those are not as strictly related, but policy gradient is, it's good to know what policy gradient means, and then we will discuss DDPG next time. But here they're discussing that there is, in general, like if you consider the loss function for policy gradient, like in policy gradient, what happens is that you have a policy function, a network, which has the policy, uh, and then you're trying to update that network directly, not updating a value function or a queue function. You're updating the pi function, which is a neural network in itself. And so the nabla, or the gradient of the pi function, of the j, or the thing, the expected long-term reward, is has this term, this term, and this term. So this term can be computed by taking the gradient of the policy network, and this term can be computed by running the episode. This is the reward. So like both terms can be computed that way, and that's how like you can update the policy network, and like it is usually used in conjunction with the critic model, and we will come to that. Then here they're discussing that usually, like, if you learn directly the RT, which is the discounted reward, then it's gonna have a high bias, uh, like high variance. To reduce the variance, to subtract a baseline, and then learn the formula. But it's not it's not necessary for today's discussion. Then they're discussing their framework. What is an asynchronous RL framework? And generally, the idea is that it's a very simple multi-threaded framework, where each Q learner works in its own thread, and because of that, we don't need experience replay. So that is what the contribution is. Um, and then they discuss four methods related to it. What the optimization algorithm they use, which is RMS prop, which is an optimizer that people use. And then they discuss their experiments on Atari, on Torx car simulator, on Vijoko physics simulator, and on Labyrinth. And then they briefly discuss what scalability and data efficiency on their methods provide, um, and robustness and scalability to like learning rates and random initialization. Is a method robust or scalable, stable, or not? And then some future work stuff. So this is how the paper is structured. Okay. So if you have any question, you can unmute yourself and ask now. Otherwise, I'll go to the presentation. Okay. All right. Let me see. Yeah. So this is okay. So like I said, I've tried to distill the information in that paper to like some sites, and we'll just discuss the sites briefly. It won't be long because I think it should be pretty simple once you grasp the major concepts. So in general, like we have this problem from, if you remember the previous paper, deep q networks, we have this problem of similar frames. Like if you have a neural network, and if you have a reinforcement learning algorithm which has an agent, and you're running this agent and it's collecting experience over time, then the thing is that in an episode, if you just use if you try to learn as you collect the frames per episode, then you will find that these frames are very similar. These visually these experiences looks very similar, and so it's hard to learn it because the data is correlated with itself, with different other frames. So it's better to take this experience, put it in a buffer, and then sample from that buffer. So that is how we achieve decorrelation in DQN and other methods. And then this method, the contribution is that instead of experience replay, multiple agents are executed in parallel. So instead of storing these experiences in a replay buffer, what you do is you have multiple threads, let's say 8 threads running, and each thread has its own frames. And then finally, like after some time, the threads are like once it's finished, the threads are joined, and at some point the gradient is computed, but because the experience is coming from 8 different environments, or 8 different threads, it makes it so that the data is decorrelated because of this different number of threads. Okay, all right. So background reinforcement learning, an agent interacts with an environment E over a number of discrete time steps. At each episode, each time step, agent receives the state ST, performs an action AT, and this action is according to a policy that it's maintaining. And in return, the state transitions from ST to ST plus one, and a reward RT is achieved. The process continues until the terminal state is reached. So you are in a state S1, you take the action A1, you reach S2, and you also get reward S1, R1. So S1, A1, you get reward R1, and then you transition is to S2. Then you take A2 and you get R2, transition into S3, and so on. Okay. Any problem? Any questions here? All right. Then what is the goal in reinforcement learning? I discussed last time. It's to maximize this long term expected discounted reward, which is this notion of reward R1 plus R2 in an episode, R in the same episode. So tau is a trajectory. So basically, you can think of it like you have an agent and you put it in an environment, and now it has to run multiple episodes, and along each episodes it can compute this expected reward. It can compute this discounted reward, and then you have to take the expectation of that across multiple episodes. So you have to increase or maximize the long term discounted reward, but an expectation of it over multiple runs. Okay. And then what is the action value function, and what is the optimal action value function? So in general, like when you have this is all discussed from last time. So in general, what is happening is that when you have a policy pi, you can create this function called qpi, which is the expected return for selecting action A in state S and following some policy pi. So notationally, we can write it as q pi of SA is the expectation of tau, and then reward Ri plus gamma Ri plus 1 plus gamma square I plus 2, and so on. Where Si, this first state in this thing, is given by this function that you're providing, and AIA is also given by this action that you're providing. So what this is saying is that the Q value of a state action pair following a policy pi is the expectation of all possible trajectories that you can take from that starting point S, where you take the action A initially, but later on you take actions according to policy pi. Okay, so you are in a state S, you take an action A1, and then later on you can take anything, but it's according to policy pi. So this branch will be if you do the expected discounted reward over this branch, it gives you Q of SA1. Similarly, this branch it gives you Q of SA2, and this branch gives you Q of SA3. So the distinguishing thing is that you're in state S, you're taking the action A. These are the only two events that you can control, and then after that the policy pi comes into action. The action is chosen according to policy pi, and the states is transitioning according to a transition function, and then whatever is the rewards that you get here plus the reward that you get here, you take the expected discounted reward, you take the discounted sum of it, and that you have to do an expectation over all possible trajectories, and that's how you compute the action value function or the q function. Okay. And this again from the last week. Uh, Q function is Q star is the maximum expected return for selecting action A in state S, following an optimal policy pi star. So what is the optimal policy pi star? An optimal policy pi star is whatever achieves the maximum reward uh, in the long term. So if you let's say know this, you don't know this function, but you know that this is pi star, there's a pi star, then the recurrence has can be written down like this. Like this, even though this part is recursive, you can see that ri plus one and so on until this is can be written as like this. This looks like the another expectation, which is like the q function from state si plus one and action ai plus one times gamma. So there is a recursion here, but uh, if you want to learn the optimal policy, then this recursion value is also the best value available. So it should be q star of si plus one and ai plus one, but maximized over all ai plus one because this is the best policy that we are following. And this is the Bellman equation where you have q star is equal to expected value over trajectories, reward of SIAI plus q star of SI plus 1. SI plus 1 is achieved by taking action AI in a state SI. And then AI plus 1 is a placeholder where you're maximizing over AI plus 1. So if you have this value, this acts as a target that you can learn towards, and this acts as your base, and you can try to make sure that your network is learning this target value. And this is the Bellman equation. Okay, any questions here? Okay. Okay, and then briefly, what is a value function? Value function is expected return starting in state S and following the policy pi. So it's similar. It's very similar to this. The difference is that you don't have an action AI here. So if you don't have an action AI here, it's just v pi of S, and then what it's saying is that you're starting in state S, and then every action you take along the path is chosen by this policy pi. So actions are chosen according to policy pi, and then you get the rewards in the episode, and you discount the rewards, and then you take an expectation across multiple such trajectories, and that's how you get the value function v pi of s. So it is the expected return starting in state s and following the policy pi. And similarly, just like action value function had an optimal action value function, which was when you follow the optimal policy pi star, the value function has an optimal value function, which is when you follow the optimal policy pi star. So that happens when uh, all of these actions that are chosen are actions chosen according to pi star. And when pi star is chosen, you are maximizing the long-term expected rewards. So it's basically q like of all the possible actions that you can take in S, it is the maximum q star action, maximum q star SA that you get out of all of these. So that is the optimal value function, and these are the two equations that people use. This is the Bellman equation, and this is the other equation. So any questions so far? Okay. So when following pi star, you get this equation, and this recurrence rule gives us QLearning equation. So this is how you do QLearning. You have your network which predicts q values, and then you take a mini batch of examples from the replay buffer, and then you compute an expectation of yi minus q of sa. Q of sa is your base value, and this is your target value, and the target value is computed using RSA plus gamma max of action a dash q of s dash a dash. So this is just this part. So what this is saying is that your q star function follows this equation. So what we will do is we will compute q star function for every s. For a given s, we'll compute q star function, and we'll make them go regress towards these target values. So this is like a regression uh, value, that regression value we're doing towards this target over a mini batch, and that gives you the loss for the parameters which you can compute autograd over. Like you can do a back propagation with respect to this loss. Okay. So note that we are doing things towards like a one step target. So what that means is that you have reward of SA, and then you go forward in one step, like because you have SA and it leads to S dash. So you need to do two passes. You need to do one pass for Q of SA to compute this value, and you need to do second pass for Q of S dash A dash to compute this value. So you're looking one step into the future. So this target is called the one step target, because to compute this target we need information for SA and information for S dash A dash, such that the S to S dash Z transition take happens upon taking the action A. And in other words, we need one step information from the future of SA. So this is one step target, but we want to do something called as n step Q learning. So in n step Q learning, what happens is we could follow the current policy for some number of time steps for n steps, and then use the maximum value here at the end of it to give us a different kind of a target. So the difference between these two targets is that in the one step target, you have just the reward at time step at the first step plus this value. But if you note that if you really see the recurrence, you will find that you can instead do it at this step as well, or you can do it at this step, or you can do it at any other future step. So the recurrence that you have at for one step, you can do it for many number of steps, and that's how you get the n step learning update. So in n step learning, what is happening is that you have a set of rewards that happen one after the other. Reward ri plus 1 till ri plus n minus 1. And then this value at the end of it is the second pass that you do. So there, you still do two passes, one pass for q of sa and one pass for q of si plus n, ai plus n. And uh, then you just compute this estimate, which is another estimate for the q learning update. And this, because you're doing n steps, it's called n step q learning, where the information about n next n steps needed to compute the targets. Okay. So this I think is new. If anybody has any questions, they can ask me. Okay. uh, so then the then we come to the crux of the paper. The crux of the paper is that they have something called as an asynchronous reinforcement learning framework, in which there are asynchronous actors. That is, each actor is running on their own thread, and each actor has its own exploration policy. And because of this, no replay buffer is needed. So we'll discuss why no replay buffer is needed. But benefits are that you reduce the training time, roughly linear in the number of parallel actors, and all policy methods can be used. So it might be confusing what on policy means, but I'll discuss what on policy means. So what is off policy and what is on policy? So off policy methods are methods in which there are two separate policies. One policy is to generate the behavior, and one is to learn. For example, in Q learning, the generating policy is epsilon greedy, which is a mixture of greedy policy and random policy, and the learn policy is updated using greedy updates. And in on policy method, the policy which is learned is also used to generate behavior. For example, SARSA. SARSA looks very much like Q learning, but if you see the update rules, you certainly see a difference. It's this part. SARSA, what SARSA is doing is it's saying Q of SA is Q of SA plus this is a target. And in Q learning, the target is this one. So Q learning is doing a greedy update, whereas SARSA is doing just a normal update, because this is the normal update you would have um, if you did not assume an optimal policy. So even though it looks like that it doesn't go towards the optimal policy, this SARS update will also converge in practice towards the optimal policy. And this in Q learning we are using greedy update, uh, which is different from the update from how behavior is collected. So why this is off policy is because this is the update used for learning, and the same approach is used for it's not, and a different approach is used for collecting experience, which is an epsilon greedy approach. Like you, for some percentage of time, you randomly choose an action, and for some percentage of time, you use a greedy approach. So because those two things are different, that's why this is an off policy method. And SARSA, where you learn this thing, you're learning what you're updating, and you're generating experience using the same approach. So that's why there's a SARSA. So SARSA actually is an acronym for state action, reward, state action. So all you need to do is you need to have state, action, the reward for that tuple, the next state, and the next action, and there is no max. So any question in SARSA versus QLearning? Okay. Yeah. So I mean, this is not like a big deal of difference, because it's not a theorem in itself, but it's very like these two look very similar, and it seems very counterintuitive why this will also like lead to an optimal policy, but it does in practice. So, but the reason it is not used is because it's an on policy method, and an on policy method because you are like generating the experience using the same thing you're learning. So it's hard to like it's hard to stabilize the learning. That's the problem with on policy method, is the learning is not stable. But in Q learning, because it's an off policy method, it is updating something else, like updating something else and collecting experience using something else. So it's easy to make the learning stable. That's what I'm saying here. So in on policy method, since the data is generated using the policy being learned, the learning is not stable. Okay. So before we move on to methods, any questions, SARSA of policy on policy methods, or what the framework is? Okay, so we have some slides, but it should be simple. Um, so okay, so the four methods that discuss is so the four methods that discuss are asynchronous one-step Q-learning, asynchronous one-step SARSA, asynchronous n-step Q-learning, and asynchronous advantage actor predict. So asynchronous one-step Q-learning. The algorithm is like this. It seems very uh, difficult to grasp at first, but most of it is actually I've seen before in the DQN presentation. So the idea is that you take an action based on the epsilon greedy policy. You receive a new state. You create a target, which is R or R plus gamma maximum Q slash A, QS dash A dash using the Bellman update. So this is the Bellman update. And then you compute the gradients for the target minus the y is the target, and the base value is this. So target minus base squared. You regress this value and you accumulate the gradients. And so what is happening is, and what is extra here is that there is a target network. So what is a target network? So because the learning is not stable, it makes sense to have two networks. One network is what you use for learning, like you use it to update the gradient instantaneously. You change its gradient at every step. And then there is a second network, which is called a target network, which changes very, very slowly. So what this is saying is that after many steps, update the target network. So if t mod I target, let's say I target is 500, then t mod 500 is equal to 0, then update a target network. So it's updating target network every 500 steps, or every 1000 steps, or every 2000 steps. So that's the point of the target network, to keep a copy of the network which is being updated very, very slowly, so that we don't so that if the original network like destabilizes, we still have the target network which can be which doesn't destabilize over time. And then what happens here is that if t mod async update is equal to 0, s is terminal, and perform asynchronous update of theta using d theta. So there is another one, there is another counter, and if uh, if this counter, if the mod of this is 0, then or s is terminal, then you perform an asynchronous update of theta using d theta. So what is happening is we are accumulating d thetas, we are accumulating d theta, but not changing the d theta. And then over time, if we need to update the target network, we update the target network. And then when we are almost done accumulating and it's time to update, then we perform a simple update and clear the gradients. So that's what's happening. And as you can see, there's no replay buffer here because all of these are happening in different threads. So that is why the gradients that are being updated are with respect to like different environment instances, and there is a diversity of different state action pairs that are being accumulated. The gradients are being accumulated over state action pairs on different threads. And then once it's time to update, the threads, the update is happening, and then the gradients are cleared again. That's what this algorithm is doing. So briefly, what is happening? The target network is being maintained and it's updated slowly. Each thread interacts with its own copy of the environment and computes the gradient of the QLearning loss. Gradients accumulated over many times before applying. And each thread has a different exploration policy, because if you set them to the same exploration policy, then they will have, like, if you're starting with the same state and you have the same exploration policy, then you don't have any diversity between the different threads. So you want to explore differently so that there is exploration diversity, and there is robustness in the learning, because you have these state action pairs from different threads which are doing different things at different times. Okay. So that and the update is one step QLearning. So this is just one step, as you can see. Okay. Any question on asynchronous one step QLearning? Okay. All right. So the next two methods are pretty similar. After asynchronous one step QLearning, we can have the asynchronous one step SARSA. And asynchronous one step SARSA, the only difference is that the target is now a SARSA target. So if you see this part here, this part was gamma maximum of this. This is the Bellman update. Instead of this, we have a SARS update, which is we take an action A, like we take an action A, like we take the state, action, reward, next state, next state, and next action from the experience buffer, and then gamma instead of max switches to gamma q of s dash a dash. This is a change target, and with this you get the one step SARSA. So any question in what is the difference between one step SARSA and what is the Q learning, one step Q learning? The target is different. Okay. And then we have asynchronous n step Q learning. So in n step Q learning, the difference is that instead of having one step update, you have an n step update, which we just discussed here. So an n step update looks like this, right? And how it's computed is basically R1 plus gamma R2 plus gamma squared R3, and so on until gamma to the power n minus 1 RT minus 1 uh, plus gamma to the power n times this thing, the max of Q function here. So how you do this is basically uh, this algorithm. So let's decompress this algorithm quickly. What it means is that as before, you have the theta vector, which and then your target vector, target parameters, theta dash, and then you start by saying you take an action according to the epsilon greedy policy. You receive a reward RT and state ST plus one, and then you compute, like after you've done the entire episode, you have to do the entire episode, and once you've done the episode, then you can compute the target. So we'll compute targets like this. For the last step, the target is simple. It's just 0, because because there is no two steps. You need at least two steps to be able to two steps worth of data to be able to compute a TD target, right? So for terminal it's 0. For non-terminal it starts with max of q of st plus 1, and then what you do is you do ri plus gamma times whatever it is, and then you accumulate the gradients for this, and then to compute the previous target you have rt minus 2 plus gamma times whatever comes here, which gives us gamma times rt minus 1 plus gamma squared times b of st. And then when you can compute the targets, you can go one by one back, and you compute a one step update, a two step update, a three step update, and four step update, and so on. And for each of the update, you will accumulate the gradient. So you will accumulate the gradient for this, you will accumulate the gradient for this, and so on until like the length of the episode. And then the rest of the part is similar. You have to update the target episode. You have to update the target according to the according to the like when every 300 or 500 or some hundred number of steps, and you have to update the in this approach they update asynchronously directly after they have an episode's data. So you collect the data for an entire episode, you compute the gradients for that episode, you do an asynchronous update using d theta, and then you update the target if needed. So any question in this asynchronous and step QLearning? Okay. And then we have the last method here, which is the asynchronous advantage actor critic, which is A3C. So there are three A's: asynchronous, advantage, and actor critic. So A3 and then C. That's the method we are discussing today. Um, so like there are two. Basically the approach goes like this. There are two networks. There is a policy network pi, which takes in a state and directly hands you the action. It gives you the action when you compute the when you produce a state. So, for example, if it's a discrete set of actions, then like a it will produce like a softmax over the values, and you will choose one of the actions. Or if it's a continuous one, that will directly give you the action. So you have two networks. One is a pi, which is a policy network, and then it's also called an actor network. And then there's a critic network, which is a value function. So the value function, the role of that value function here is to say whether or not you're doing things correctly. So it gives you whether or not you're in the reward of the best reward you can obtain from the state is, right? So you're updating these two simultaneously, and this actually comes from actor critic networks. Actor critic networks is another paper, but in general, the structure comes from actor critic networks. And in actor critic network, there is an actor network and there's a critic network. And the actor networks and critic networks are very different using different rules. The critic network is updated using the Bellman rule, and the actor network is using the policy gradient rule, which we haven't discussed, but I will discuss it next time. But the policy gradient rule in general, it looks like this. You have to update the policy network by policy plus some gradient, and this gradient is computed. If you don't take the expectation, then it's computed like the gradient with respect to pi of log pi. So I know you don't see how the log comes in, but you can see it as soon as you have seen the policy gradient theorem. uh, and it's a long proof, so I've kept it for next time. But in general, like this part multiplied by the return is what we use. But there are many variants of this approach where you instead of using the return, you use the advantage. And the advantage is the q function minus the value function. So here we're using the n step q function minus the value function, and that gives us the advantage function. So so briefly, there are two networks. There's a policy actor network and there's a value critic network. The policy network is updated using the policy gradient theorem. The critic network, the value function is updated using the Bellman update. And you can see it in the algorithm here. It's pretty much the same as n-step actor critic, but instead this time it's slightly different in how we accumulate the gradients. So basically, you start and collect an episode, and then you compute the n step return. But as you are computing the n step return, you are accumulating gradient with respect to the policy network theta dash and the value network theta dash v. And the difference is that the active network is has this log term and this r minus v, which is the n step return, minus the value function, which is the advantage function. And the second one is a regression loss, or the n step return minus the value function. So that is simply the q function that they're using here. And so they are updating the critic network using the Bellman update here, the second one, and they are updating the policy network using the policy gradient approach. And then after they have done that, they have performed the asynchronous update of both of them using the gradients that they have. And then they will collect another episode, do the things again, and so on. And note that this is happening in the different threads. So sometimes the gradients are being accumulated from different threads as well. Okay. So any question in asynchronous advantage actor critic? Okay. Yeah, it does seem very daunting at first, like how did they come with an approach like this? But if you like read through it a little bit and you try to see what they're doing, it's pretty simple. uh, uh, like if you've spent some time playing with the reinforcement learning framework, uh, like usually it's just some Bellman update that they're doing, and after they've done the Bellman update, they're doing asynchronous updates. So mostly like things are like in value function methods, they are usually Bellman updates, and then there's a policy gradient. So they're like two major pieces of reinforcement learning are the policy gradient theorem, the policy gradient updates, and the second one is the Bellman update or the Bellman equation. So once you know these two parts, like you've covered like a lot of reinforcement territory in terms of how to update parameters and learn those parameters to play games. Okay. So any questions so far? And if not, then I'll continue on to the results. Okay. So in general, the results are promising. As you can see, the yellow line, the A3C is the yellow line, and it is like the highest among all of these. That's why the A3C is the most celebrated algorithm for this paper. But the other ones like DQN is the most common, the baseline they're comparing against. And DQN is normal. It's similar to the other approaches. It doesn't see very, it doesn't do very well compared to A3C. And these are 5 different games in Atari. So be the same games that they used in um, the actual 2013 paper. So these are the benefits. This is a clear advantage in A3C compared to other learning methods. And then this is the training time that they have. You can see that A3C, it requires 1 day on CPU. Like these methods require 8 days on GPU, 8 days on GPU, 4 days on 100 machines. So like these are very high intensity, high computational methods, like with lots of computational overhead. But A3C requires 1 day on CPU or 4 days on CPU or 4 days on CPU, and needs like a good increase in the values. So like this is why this method is very preferred. Okay. And then we have some videos we can quickly see. So the other results are like for Torx. Torx is a car racing simulator. We have to win a game. So as you can see, like in the Torx racing simulator, they are able to uh, like right now, not seeing how it overpasses the goes past the car, but now you can see it goes past the car and comes first. So it's like this is one of the results they have, one of the videos they have. Okay. Then in Mujoko Physics Simulator, they have another result in Mujoko Physics Simulator where you're given certain tasks. So every robotic arm is task. Like for example, this is a cardboard task. In a cardboard task, you have to balance this pole, and you can see it balances the pole perfectly, almost perfectly. In this you have to walk. It's a physics simulator where this in this task you have to walk, and it can walk. Then in this one, it has to move. It has to use its leg to move, and it is able to. It is not. It is able to move. In this one, it is able to move around as well. So these are all learned through E3C and other asynchronous method. This one it's a balance. I think it's a move as well, but they're not showing that part. And this one they're supposed to correct the green and go towards the red. This is the pictorial representation of what it sees. So it's slightly blurry for what the algorithm sees, but we see the actual rendering. In this one, it has to go and move it toward the red square, red cube. Okay. So this is the second simulation that they have. And the third one is this labyrinth environment, which is another application of their approach. So in this, you're given a point to collect apples and different fruits, and you can see it is able to collect apples and other fruits. So yeah, these are all trained using convolutional networks and simple A3C algorithms. Okay. So briefly, those are the methods, and then to conclude, there are some points. So these methods are like scalable and data efficient. As you can see, using multiple threads leads to gain in speed up. Like this is the speed up that they're showing in values, and the speed up is defined as a formula. A speed up from using n threads is defined as the time required to reach a fixed score using one thread divided by time required to reach the reference score using n threads. So if you require less time, then how much less time you need? So this requires 3x less time, this requires 6x less time, this requires 13x less time, and so on. So you can see there's a speed up of as you increase in the number of threads. And then they tried the approach with 50 learning rates and different random initializations, and it was very robust because the method was always leading to good scores. Therefore, they said that the approaches are robust to a choice of learning rate and random initialization. And in conclusion, what we can say is that the approach has parallel training and it stabilizes on policy methods and other off policy methods without the need for experience replay. And incorporating experience replay could even lead to more speed up. So that's what this entire paper is about. So any questions on this paper? These are the index. I'll stop at the index and you can think about it and let me know. Otherwise, I'll quickly discuss what the other homework is. Okay. Any questions? If not, I'll quit. All right. So I think nobody participated from the last time. So what I'm going to do is increase the stakes a little bit. So people who are already here, we had this DQN uh, thing last time where I said that you had to implement DQN. Like I'd already given the basic code for start a code for card pool, and all you had to do was apply it on one of these environments, Pong, Breakout, and Space Invaders. And what you need to do was change the network and train. And then whosoever did it first would get the homework for $25. But now I'm making it $50. So whosoever can get this code working, if you want to note this down, its code is little simple to learn, like it's bit.ly I'll code. And if you're able to this is just a repository I have with simple implementations. And if you go to this file, it's already given like how to use it. Like I've created a very simple thing that learns on cardpool, and all you have to do is to try it on one of these Atari environments. And if you can able to do that, I'll give you a $50 Amazon gift card. um, and if nobody participates, then we will increase the stake again. But if somebody participates and even tries, even if they're not able to do it and they tell me, then I'll give them $50 if they want. Like, it's all on trial. If you try, even if you're not able to get to it, I'll give you $50. So, but it's there's only one gift card so far, so it depends on who does it first, and also who does the most effort over the entire next week. If nobody does it, then we will ramp up the price. If somebody does it, then um, they will get it, like based on how often, how much they have worked towards it. Even though they are not able to do it, that's fine. But I think they should be able to do it because it's pretty simple in terms of, if you just read this file and try to implement, instead of doing a linear, you do a convolutional network using Torch, then you can get this $50 price. Okay, so that I'm not giving any homework in A3C because I don't think people have even attempted the BQN one, and so I'll give the I'll give the prize to people who attempted DQN one first. Okay, any questions? Right. If not, then I'll stop recording and I'll see you guys next week at the same time. And the next week we will discuss uh, DDPG and policy gradient. Okay. Right. You guys have a good weekend, and yeah, see you next time.